Hi guys, and welcome back to my channel. In this video, we'll be talking about, or we'll be deriving the potential energy for sort of an infinite one-dimensional ionic lattice. So we talked about the potential energy formula for ionic compounds in the last video, and we talked about how there's this sort of A factor, which is called the Madelung constant, and this is different for different crystal setups, right? For different crystal structures, we have different values of A, and the crystal structure is the only thing that defines the value of A, and the entire rest of the equation is pretty similar to what we've seen as a potential energy equation. Now, in this video, we're basically going to derive that potential energy expression and see what the A value is for a one-dimensional infinite lattice, so this specific crystal structure. Okay, so let's just get right into it. So we have these two ions. We have a cation and we have an anion. We're going to call the big one the anion and the small one the cation. And let's only look at a cation right now. So we're going to only look at the cation first. And you can see that this cation has a charge of plus z, right? Plus z. That means that the actual charge of the cation is not just z. It's the actual charge, q cat, is plus z times the charge on an electron, right? In coulombs, if I want the charge of our cation, it's z times the charge of an electron. Z is the amount of electrons it's lost, and then we got to multiply that by the coulombs of an electron. Similarly, our q anion is minus z times E. Okay, so that's our first setup thing. Now we want to look at, we're looking at our cation, right? We're going to look at only the right side of this cation, right? So it's an infinite lattice in the right direction and in the left direction, right? So we're going to look only at the right side, and then we can just take that potential energy that we get only from the right side and multiply it by 2. Why can we do that? Because the left side is exactly the same. Remember, it's just an infinite lattice in both directions. So the left and right side of the sodium cation is going to be, or not sodium, but the cation is going to be exactly the same. So we're only going to look at the right side, derive the potential energy based on the right side, and then multiply that value by 2 to find the total potential energy on this of this cation. So let's look at our Coulomb's law equation, right? We know that potential energy, U equals 1 over 4 pi epsilon naught. This is our K constant times Q1, Q2 over the distance between the charges. So first we're going to look at the right side. So we got to look at our cation and our anion. First, that first interaction, right? So if we look at that first interaction, I'm going to write potential energy is equal to our 1 over 4 pi epsilon naught times, I'm going to factor this out, so I'm going to factor that constant out, Q1, Q2 over R. If we look at Q1, Q2, that's our Q cation times our Q anion, because that's the two interactions we're looking at, the cation and the anion interaction. So that's ZE times negative ZE, and that should get us negative Z squared E squared, right, if we're just multiplying those two values. And our distance, we can see, is, on this diagram, it's D. Now let's look at our next interaction to the right. Right? We have this sodium, but not, we're looking to the right. We just saw the interaction with the cation, or the anion. Sorry, I keep calling the cation sodium, but it might not be sodium. We see this cation, right? We just did the interaction with the neighboring anion. Now we look 2 down, and we see this other cation. Now we got to look at this interaction with that cation, right? The cation-cation interaction. So we have 2 cations, so that makes our Q1, Q2, right? That's just going to become Q cat times Q cat again. So that becomes just positive Z squared E squared, so we have plus Z squared E squared. And then we divide by our distance between the two, and what is the distance between the two sodiums, or the two cations? We have our distance here, and we have the distance here. So if we add those two distances between the cations, we get 2D. And you can sort of see a pattern now. We can do one more. Next, we have our sodium interacting with this anion, or our cation interacting with our anion, again, but at a different distance away, right? So we have again, we have, when we multiply our charges, we get minus z squared e squared, but our distance away is going to be d, and then one more d, right? So we have 3d for our distance away. And we can see that this is going to continue because it's an infinite lattice. And we note that we can factor something out, right? Let's look at our potential energy and let's factor z squared e squared over d. So we get z squared e squared over 4 pi epsilon naught times d. Then we do minus 1 plus half minus 1/3 all the way, right? You keep going. And we can also factor out a negative sign, so I'm just going to take a negative sign out. We put the negative here, factor out the negative sign like that, right? Okay, so now we can sort of see something. This is like an infinite sort of series, right? It's an infinite series. Infinite series. And if you know Taylor series, you might recognize this from our Taylor series of log 1 plus x or log 1 minus x or something like that, right? And you don't have to know this, but if you look at the Taylor series for log 1 plus x, you might see a way to relate this series to log 1 plus x. And you are correct. If you know Taylor series, that's good. If you don't know Taylor series, don't worry. This sum actually turns out to be log of 2, natural log of 2. So if we now just rewrite this, we get negative z squared e squared over 4 pi epsilon naught times d times our log of 2, right? And this is when we looked for the potential energy only to the right of our cation, right? But remember, we said that there's also interactions coming from the left of the cation, and those interactions are exactly the same because it's basically a copy and paste of what's on the right. So we just got to look at the left side, and we just got to take our potential energy and multiply it by 2, because that's just going to be what's on the left side that's added to the right side, right? Because the left side is the same as the right side. So our actual potential energy is multiplied this times 2. So we get minus z squared e squared over 4 pi epsilon naught d times 2 log 2. So this is per cation what the potential energy is, right? But say we want the potential energy per mole of cation, right? We want per mole of cation. What do we do? If this is per cation, because we only looked at one cation, remember? So if we want per mole of cations, per mole cations, we just got to multiply by Avogadro's number. So we do minus our Avogadro's number times z squared e squared over 4 pi epsilon naught d times our 2 log 2. And this should be looking really, really familiar to the equation we saw on the previous video, in the previous video. So now we got to look at the anions, right? Because we looked at the cations, we looked at per mole of cations what the potential energy is. Then we got to look at per mole of anion what the potential energy is, because both of these contribute to the total potential energy. If we look at the anions, though, you might see that this is exactly the same as when we looked at the cations. So let's take this anion, for example. And now we want to calculate our potential energy. So we set up this equation, 1 over 4 pi epsilon naught times, now we're going to, again, only look to the right, because the left is the exact same as the right. So we just need to multiply our value by 2 at the end. If we look to the right, our first value is going to be the product of the charges. So if we take this anion and this cation, we get minus z squared e squared, and then the distance is is d. So we get this term, right? We get that same term. Now if we look at the anion interacting with another anion 2d away, we get minus ze times minus ze all over 2d, which just becomes positive z squared e squared over 2d, which is this same value. And you might see a pattern, right? It's the exact same thing as our cation potential energy. So we know that our potential energy for our anions is the same exact as our potential energy for our cations. So E potential per mole of anions is equal to the same exact thing, negative Na z squared e squared over 4 pi epsilon naught d 2 log 2. And now we have our sort of final, now we got to take these two values and find the total potential energy of this system, right? So if we're thinking about the total potential energy, we might just think, okay, we have our potential for moles of cations and our potential energy for moles of anions. Let's just add the two, right? That should be our total potential energy. But we actually got to add the two and divide by 2. We gotta take half of the sum. And why is that, right? If we think about when we did our derivation for cations, right? We took, okay, what is this cation's interaction with that anion, right? We looked at this interaction when we wrote our equation there, right? But when we look at our anion's interactions, we took this guy, and when we're looking at the left side of the anion, right, we asked, what is this interaction here? We asked the same question twice, basically, right? So we're double counting the potential energies. So just to explain that a little more clearly, when we looked at our cation, right, we asked, okay, what is the potential energy contribution when we have this anion, right? How is the potential energy changing when we have that anion? But when we looked at our potential energy for our anions, right, and when we were looking at the left side, because we multiplied our right side value by 2, that means we're accounting for the left side. We also asked the same question, what is the potential energy that is caused by this cation being next to that anion? So we've asked the same question twice, basically, and this means we've double counted. And because we double count, we just need to divide our final answer by 2. So hopefully that explanation made a little bit of sense. When we want our total potential energy, so I'll just call it total, we add these two and divide by 2, and if we add these two and divide by 2, we just get negative Na z squared e squared over 4 pi epsilon naught d times 2 log 2. Oops. Because when you add these two, you get 4 log 2, and then you divide by 2, you get 2 log 2 again, right? So this is our total final answer for our total potential energy. And, right, what is our A value for this system? Our A value for the system, if we remember our previous equation, our A value is this constant that's sort of out front from this main sort of equation, right? Our proportionality constant, basically. So our A value for this one-dimensional lattice, right, for this one-dimensional infinite lattice is 2 log 2. So hopefully this video was interesting. I just wanted to show how you actually derive that potential energy formula for a sort of relatively simple system. When you get more complex systems, it's really hard to derive this formula. You're just given the A value and you just work with that A value. But I wanted to show, okay, where does this A value come from and how can we derive it in a semi-simple system? So yeah, thank you so much for watching, and I hope this was informative. I'll see you guys in the next one.